Hi, welcome to my channel JaberTime. Today I'm going to go over integration by parts, and I do have 5 examples to go over, as you could see listed on the screen. Let's get started. Integration by parts. Where does it come from? The product rule states that the derivative of the product f times g equals f times g prime plus f prime times g. So if I rearrange, I put this next to this term, and I leave this alone, f g prime by itself, and I switch everything left and right, I do have the following. F times g prime by itself equals the derivative of the product minus f prime times g, as you could see. Applying the integration to both sides, we get the following. The integration of f times g prime will equal f times g by itself, because the integration of this will cancel it. We'll leave f times g by itself, minus the integration of g times f prime. That's this part, of course, with respect to x. Now, sometimes in short we don't write f of x and g prime. We write it this way. Integration of u dv, as if this is dv and this is u, will end up u, that's the same f right there, which is u, times g. If this part is dv, v will be g by itself. So integration of dv will take you back to v. Integration of g prime dx will take you back to g, minus the integration of g, and g is v, f prime dx will be du, because we called f of x u. That's kind of in short. To remember how to set it up, I have the following. You have u, and you have dv, u and dv. Differentiate u going down this way, that will give you du. Integrate dv going down will give you v. Then you just multiply diagonally this way. That's uv, that's uv on the side, minus, you go back this way, minus the integration of v du, minus the integration of v du. That's where the integration by parts comes from. So we have u v prime, the derivative of u times v, the product rule, will give you u v prime plus v times u prime. Once you find the derivative of v, once you find the derivative of u, and you alternate, and you end up with the sum of these two terms. Integrating on both sides, we will have the integration of u v prime by itself equals the integration of this will give you uv minus the integration of v du instead of u prime. Now, how to choose the part that is called u? This is mainly the practice that comes with integration of by parts. You need to know which one to pick for u, and the rest will be dv. Once you have picked the u part, everything else is going to be called dv. Here's a quick note to help you remember what is u and what is dv. L for logarithms, that's like log x. I for inverse trig, that's like tan inverse. A for algebraic, that's like 5x squared plus 4. T for trigonometric functions, like cosine x. E for exponential, like 10 to the power x. So we go in order, and we pick u as it refers to the word liate, like layette. Doesn't work 100%, but most of the time that's how it works. Let's go for example number 1 and see how we could apply this. So example number 1 has a function times another function. This is algebra or algebraic. This is trig. To remind ourselves, algebraic goes third level and trig goes right after it, a and t. So we're gonna pick u for x, and the rest will be sine x dx, the trig function, with dx will be dv. U will be x, and dv will be the rest, which is sine x dx. Applying this format, easier to remember, the integration of dv will give you v, and the derivative of u will give you du. Derivative of x will be dx, 1 dx, in other words. The integration of dv, which is the integration of sine, will give you minus cosine. Let's take this off and apply this right here. So we have x times minus cosine x, and we go back this way, minus the integration of minus cosine x times dx. As you could see, that's u times v minus integration of v du. You don't have to remember this. If you could set this part right here and multiply and go back, multiply these two terms under the integration with the minus sign. Minus and minus will change it to plus. We'll arrange this and write it negative x cosine x. So now we're almost done. We just need to simplify this part, the integration of cosine, which is sine, because the derivative of sine is cosine. Of course, we don't want to forget the constant of integration. Minus x cosine x goes down. Integration of cosine is sine x plus c. And that should do it. Let's go to example number 2. The integration of ln x dx. Now there is nothing much here to think about. What is u, what is dv? So we're gonna pick u ln x, and dv will be the rest, which is dx by itself, like 1 dx. Differentiate u to find du. That's a derivative of ln x, 1 over x dx. I mean, we have the dx on this side to make it happen. It's like du dx equals 1 over x. And the integration of dv will give you v. The integration of dx will take you back to x. Or the derivative of x will give you 1. Just multiply and go back this way. Multiply these two with the integration and the minus symbol. And that goes right there. X multiplied by ln x. Instead of writing ln xx, we write x times ln x minus the integration of x multiplied by 1 over x dx, as you could see. Well, this one simplifies and goes quick. That's a 1. So we have x ln x minus the integration of dx by itself. We're almost done. That's a minus. That will give you x. We don't forget again the constant of integration. We're done. Example number 3. The integration of t squared e to the power t dt. Now here, this is a different problem. Notice that t to the second becomes simpler when differentiated. It goes to the first degree, and if we differentiate it again, it goes to a constant. So usually we pick the function u, the part that, or the term that gets reduced or simplified, gets simpler. Where e to the t, the second part, is unchanged. The derivative of e to the t is e to the t, so it's not gonna go anywhere when differentiated or integrated. So we choose u to be the one that gets simpler. That's t to the second. Apply this idea, this format. U equals t to the second. dv is the rest, which is e to the t dt. Derivative of this will be 2t dt. Integrate e to the t gives you just e to the t. Multiply and go back. Multiply these two with a minus and integration. I have the following. This is the problem, and this is the answer. T squared multiplied by e to the t minus 2t multiplied by e to the t dt. Now this part here is in red. We're not done. So we need to work on this one and find the integration of this. We're going to do it again by parts. The integral t e to the t dt is simpler than the first one. So we have some accomplishment, but we're not done than the original, but it's still not obvious. So therefore, we use integration by parts a second time. Let's take it up here and do it right here. The integration of t e to the t dt, I kept it in red up here, as you could see. We're going to apply the same idea. This t gets simpler, so we're going to pick it as u, and e to the t dt will be dv. Derivative of t will be just 1. Of course, we're going to write dt, so we could end up being able to write it correctly with integration and dt in the way. The integration of e to the t stays e to the t. Let's apply this right here. T times e to the t minus the integration of e to the t multiplied by dt. The integration of this is going to stay the same. I have the minus. Bring this down, bring the constant of integration. Okay, now we're almost done to finish the problem. So what's the problem? Well, it's this part. So I have it right there. On the first part, on the first step, we get this part. So I'm going to rewrite this, and instead of this portion right here, we're going to write this part here. Here we go. So we're back to this. And we solve this part up here. Let's replace it. Minus 2 times t e to the t. I got it from here. Distributing the minus 2 to everything. I have minus 2t to the et. Negative and negative will change it to positive. 2e to the t. Minus 2 times c is minus 2c. But that's a constant. So we're going to rewrite it as c1 and finish the problem. Everything is the same except we wrote minus 2c as c1. So c1 is a constant of integration where it refers to minus 2c back here. 2 more problems. We're done with this problem. Number 4. The integration of e to the x sine x dx. Notice that neither e to the x nor sine x becomes simpler when differentiated. So we have to try. Sometimes if it doesn't work, we switch them again. We switch everything u and dv, and it's going to work out most of the time. So let's try e to the x to be u. This part is u, and this part right here is dv, sine x dx. Derivative of e to the x is the same. The integration of sine x will be minus cosine x. Because the derivative of cosine is minus sine, we're missing the minus, so it has to show somewhere. We'll put it right there. Apply the same concept, multiply these two, and go back this way. Multiply these two with a minus integration symbol, and that's what we have. E to the x times minus cosine x. We'll put the minus up front. E to the x cosine x minus the integration with another minus in the way when you multiply becomes plus e to the x and cosine x right here. This is another one similar to this, so we're not going anywhere, but we need to integrate again by parts. So let's take this blue part to the side and let's finish it. We'll take e to the x as u. Cosine x dx will be dv. Derivative of e to the x will be e to the x. That's going down. Integrate this part will give you sine x. Multiply these two and apply the same concept. I get this. Bring this black portion down, plus here, and this part here, after you do it, we end up with e to the x sine x minus the integration of the product of these two parts, which is e to the x sine x. But something interesting in this problem, which is the following. I wrote everything. That's a problem. and I wrote everything right here, except I colored this one in red, just like what we were given. So it's kind of like takes you back and forth. So we're going to move this to the left, group these two terms, becomes two of them, equals this right here in black. Divide both sides by 2 to leave what we have as a problem by itself, and that's the answer. We're done. So 1/2 e to the x, if you want to pull e to the x outside as a common factor, sine x with a positive, cosine x with a negative sign, and let's put a constant of integration at the end because we don't have limits right here. We don't want to forget the constant of integration. Okay, last problem, number 5, integration of tan inverse. How do you do tan inverse? Well, we're going to take, we don't have many choices here. We're going to take u as tan inverse x. The rest will be dv, which is just dx by itself. The derivative of tan inverse x is dx over 1 plus x to the second. The integration of 1 dx will just give you back x. Let's apply the same concept right here for pi parts instead of remembering the whole formula. We get this multiplied by that, which is x tan inverse x, minus the integration of this multiplied by this, which is now x on top over 1 plus x to the second dx, from 0 to 1, from 0 to 1, and this part here from 0 to 1. Plug in 1, we get 1 times tan inverse 1 minus 0 times tan inverse 0. That's right here. Minus the integration as is. Tan inverse 1 is pi over 4, the 45 degree, and tan inverse 0 is 0 degree. Tan 0 is 0, and tan pi over 4 is 1. So that will give me 1 times pi over 4, and that will give me 0 times something is 0. It's actually 0 times 0 here. So we end up with what? Pi over 4. We don't have to write the minus 0, minus the integration. This integration, we'll take it to the side and finish it. To evaluate the integral, we use the substitution. We take this lower part, the denominator, to be called t, which is 1 plus x to the second. Since u has another meaning in this example, we're not going to use what's called the u substitution and call it u. We are using u and dv in the problem, so we end up using t instead of u. Now, if t equals 1 plus x to the second, the denominator right here, we have dt equals 2x dx. And the limits were from 0 to 1, that's x's. And of course, if you simplify, x dx divided by 2 divided by 2, you end up with x dx by itself, dt over 2. You will see why I kept x dx by itself in just a minute. When x equals 0, we're going to change the limits because we changed the letters or the variables from x's to t's. You'll see just in a minute. If x is 0, that's x equals 0, and that's x equals 1. What happens to t? T becomes 1 plus 0 to the second, which is just 1. So that's my t1, that's my x1. x2 is 1. T becomes 1 plus 1 to the second, which is just 2. Now, this is the problem clearly with x's. X equal and x equal. If I change it to dt and t variable, you're going to see the following. Notice I pulled the x to the side next to the dx, so I could take advantage of this and replace it with dt over 2. So the problem now with the variable t is the integral from t1 equals 1 to t2 equals 2, that's the 1 and 2, the new limits, of 1 over t. When you pull x to the side, that's 1 over t, and x dx is now dt over 2. Let's take the half, because this 2 is not 2, it's half, up front, out of the integration, and integrate dt over t. Well, that's going to be the natural log we don't want to be we don't want to forget that it's going to give me the absolute value, which is not going to make any difference because we're plugging in 1 and 2 where they are positive values. Plug in 1 and 2 to evaluate 1/2 outside, so it's going to end up len2 minus len1, and len1 is 0. We know the log functions, normally they go through 1, and they have the y-axis as the vertical asymptote. So that's a 0. Now we have 1/2 multiplied by len2 minus 0, which is just 1/2 times len2. Finally, to finish the problem, let's box it right here. The integration of tan inverse x dx is pi over 4, we don't want to forget this part, minus this integration, which we did it on the side, and gave me half len2. len2 over 2. That should do it, and we are done.
Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.